introduction, Georg is a philosopher. This combination is always the best. Philosopher, neuroscientist, and a psychiatrist. It's just so good. Like already good. Good start already for me. And then he's holding degrees in all of them. And then his lab is mainly focused on why and how does our brain construct the self and consciousness. But then he wrote many books on these topics. So you can actually, if you go to the website, you can find pretty much like all of them and the summaries and a lot more. Like he has all the talks and podcasts there. So it's really good actually. You can go check them out. But today, specifically, we're going to talk about, I mean, he's going to talk about intrinsic neural timescales, and we're going to ask questions at the end. Just so, again, people know, we are recording and we will upload this on YouTube. So usually the way it goes is that the questions are at the end, just so that you're not on the recording. But if you don't mind that, and if Georg doesn't mind that, of course, you can also ask during the session. So it's just really up to you, Georg. But with that, yeah, the whole stage is yours. Looking forward to it.
Okay. Yeah, thanks. Thanks for inviting and hello to everybody. So I talk about something, a really different view of the brain in terms of time. And you see it here on the left. I consider the brain really primarily in terms of time. And I say that cognition and its mental features are shaped by the inner time of the brain. What do I mean by time? I mean, here already right here is about time scales. So here you see in geology, you see vastly longer time scales than we have, for instance, in our brain. And I'm interested in the time scales of the brain. And I will say later what exactly time scales are. But before, I just want to give you the larger background framework in which I'm operating. So I think we have excellent knowledge about different forms of cognition, basically the upper layer of the iceberg. But we don't really know where and how these mental features are coming from. Yeah, mental features, sense of self, consciousness, mental disorders, schizophrenia, psychosis. And the main hypothesis is, and there's a lot of also in the recent neuroscience, particularly in animal neuroscience, that you have a global view of the brain. You look at the global dynamics, you look at topography, dynamics, pattern of change over time, topography, the regional, global organization structure of the different regions network. And we know that they somehow relate to consciousness. That is excellent work. But however, how exactly are these mental features, your experience, your subjective experience, mediated? And that's exactly the question for the how. Yeah, we are missing, philosophers speak of an explanatory gap. We are missing something in there, an intermediate thing. And that's, of course, no surprise when you hear this from me. That's where time and intrinsic neural timescales come in. And what we developed over the last years is really say, look, we do not look for something that is special in the brain for consciousness, like a special regions, anterior, posterior cortex, like in the Nature paper last year. We look for what brain and consciousness share. And that leads me to the timescales, to time and space. And here my dynamics and topography. This talk focused mainly on the dynamics, and dynamics is a wide concept, a pattern of change over time, which can be measured in different ways, scale-free dynamic time scales, entropy, complexity. Here I focus on the intrinsic neural time scales. So overall model is the background model I have here, feature of a more general brain-mind model is from neural to mental timescales through temporal integration. Yeah, so I show you that timescales are key in mediating the link from neuronal to the mental. And then I try to show you also some mechanism where we converge the imaging with computational model. Obviously, this is all first steps, so please don't kill me if you don't see the kind of causality which is there, but we're really working on that. And it's all the larger conceptual background of this common currency. The timescales are both in neuronal and mental features visible. So in my talk will be first about what are intrinsic neural timescales. So I give you a short overview, and then I give you two key features. So I focus here on consciousness. We have a lot of work on timescales and self, which is on our website, but here I focus on consciousness. INT shapes the level of consciousness and also shape the content of consciousness. And I give you some empirical data on that. And then in the fourth one, I try to get tentatively into some of the mechanisms underlying the role of timescales in the neuromental shaping. Key mechanism here, temporal integration and recurrence. And for that, I go both to imaging data and some computational modeling. So that gives you an overview. And I start with what are intrinsic neural timescales. So what are timescales? So timescales is the time allowed for or taken by a process of sequence or events. For instance, here I illustrate the heartbeat. Heartbeat is a 1 second timescale plus minus with some variance. Your breathing timescale is much longer, one breathing cycle. And you can already see in the brain, we have also timescales with the different frequencies. So here, my example of the geologic timescales. And here you already see the way I approach it. I say, look, timescales are not specific to the brain. They're not specific to mental features. They are abundant, ubiquitous in nature with different durations. Yeah. So that's a thing. And then how about timescales in the brain? So the pioneering work of the group by Hasson, who introduced the temporal receptive windows. And that's basically the duration of time in which two sim can be processed together during a task state. For instance, he showed that the different temporal receptive windows for words, let's say more in auditory cortex, and for sentences or paragraphs in much longer temporal windows in more higher order transmodal regions. So, and he measured that. How did he measure that? He measured that mainly through intersubjective correlation. So they presented words, they presented sentences, story, narratives, and then linked where the different subjects, fMRI, brain activity correlated with each other, the intersubject correlation, and then see, okay, and he saw that they really correlate in auditory cortex with respect to words. And he did also very ingenious shuffling techniques. Here, the paper is from the figures from an earlier paper. And the idea here was that temporal receptive windows are similar to spatial receptive fields. So basically, the outreach to which activity at one time point can be related to activity with other time points and to mediate a particular cognitive content, like words, sentences, music, melodies, and so forth. So that's basically the task state-based or cognitive version of timescales in the brain. So now, then there was also parallel observations in the resting state, that we have already timescales in the resting state. And here you see the definition slightly shifts. The time window in which prior information can affect the processing of newly arriving information. How can we measure that? Through autocorrelated fluctuations. I will come back to that in the neural activity in the absence of task state. And that was mainly stipulated by Murray et al. In monkeys in cellular recording, where he looked for the task-free intervals in his intracranial recording data. In an earlier paper by Honey et al. 2012, a neuron also showed that these fluctuations, these temporal receptive windows, the longer they are, the more related they are to slow frequency fluctuations. So that already set a stage here. And then basically it somewhat developed in parallel. And here, lower right, I have a figure from the Murray et al. Paper, which for me at the time when I read it was extremely inspiring. So here on the y-axis, on the x-axis, you see the intrinsic neural timescales measured through the autocorrelation window. As I said, the next slide will be about that. And the duration of that autocorrelation window measured in the task-free interval correlated with the behavioral timescales of reward. So the monkeys had to do a reward, and they measured the timescales of the reward. And you see here the different regions. And that was really very, took a basic for me, because I said, wow, maybe there's a temporal relationship between the temporal features of your resting state and the temporal features of your behavior. So that was 2014. And then I said, maybe what the neuronal and the behavioral level share are their timescales. Maybe not one-to-one, but there's an intrinsic temporal relationship. So that led me conceptually to later in 2020 then assume, okay, there's shared features, temporal features, the common currency of neuronal metals. So this was really instrumental in that. So, and since then there have been many studies, excellent studies by Zerati, Manea, Chaudhuri about intrinsic neural timescales in the resting state. And we then really focus on how do the timescales in the resting state shape the timescales in the task state and the behavior/mental timescales. And you see a lot of papers on ours on intrinsic neural timescale and memory, intrinsic neural timescales and attention. So we really try to make that bridge. So another very interesting issue in the INT, and I already indicated that, is the convergence of intrinsic neural timescales and temporal receptive window, rest, and task timescales is really they show a shared topography. Yeah, so the temporal receptive windows for words are short, obviously, and they're related to auditory cortex, unimodal regions. Whereas higher, longer timescales during paragraph and sentences are more related to default mode network regions. And that's exactly what you can also observe in the resting state topography of the INT, of the intrinsic neural timescales. You see exactly the same thing. And I indicated that here, and that goes for both EEG, MEG, as well as for fMRI. And that's important. Why? Because fMRI and EEG, MEG have different timescales. fMRI operates on an infra-slow frequency domain, meaning 100 seconds to 10 seconds. EEG operates on a much shorter timescale range from, let's say, 1 second to 10 milliseconds. But you see the same topographic distribution in both. I didn't show you the MEG data, but we showed it in a paper in 2021. So meaning there's a convergence of your time scale range, short, long, with the topography, unimodal to transmodal regions. Yeah, and that's, I mean, it's a general, probably for physicists, it's completely trivial. Time and space always go together. So, question, how can we measure the brain's INP? So one thing is here, I show you here, upper left, you have two time courses, and basically the same time course, you shift the time course, you measure the legs. So this is the original time course, and you shift it by one leg, and then you correlate the time courses over the time legs. And that gives you what is indicated here, an autocorrelation function. So this is a typical measure, and then you usually defined by 50% the autocorrelation window, but you can also measure it zero when it crosses the zero line. We also measure it now by the decay function. So we have introduced different measures to be more variable. So these are, and then you get something like this. You get an autocorrelation here, the different legs, and that's basically what you call autocorrelation window. So these are model-free ways of analyzing the ACW, the autocorrelation window, the timescale. But there are also other models introduced by Zerati and others, model-based, where you use a Bayesian-based model of that. I don't go into detail that, but I refer to a recent paper of ours where we published that as a Julia package. One of my really, really clever students, Yazir. He's really, if you ever meet him, it's an event. The guy is really clever. It's amazing. Yeah. So that basically finished I hope I gave you an idea what are intrinsic neural timescales. And the resting state is different windows, topography. So now the question, what on earth are these timescales good for? Why does the brain have this variety of timescale? And we even showed that they changed over time. There's sorry, high variability to the length of these timescales. So, and I show you some results here that the INT shape, particularly the level of consciousness. You know, the debate about consciousness is a complex debate, to put it mildly. And, and but here, I think one key feature is that we really need to properly distinguish between different dimensions of consciousness. Yeah, it's not just consciousness as a whole, but really, and here I make a first attempt into that, is the level of consciousness as basically your level of arousal to which you're awake. So, and that can be studied in different where you lose consciousness. It's an indirect way where you can study that. Here, this is an EEG study. I show you data from an EEG study where we measured the autocorrelation window in the above mentioned way. And we show considerably longer time scales in unresponsive wakefulness state. You can see this here. We also show this in anesthetic state. And interestingly, that's very important. You already see a certain differentiation in the degree of your autocorrelation window. It becomes much, much longer in the sevoflurane anesthesia and not as long in the ketamine. So that's already an indicator. Maybe your time scales are an index of different levels of consciousness. And that's exactly what you expect also from a scientifically reasonable marker, but also clinically, because you also ultimately maybe also want to use it for clinical purposes. So, and then we also did this in sleep. And you can really see this very nicely, an almost parametric increase from N1 sleep, N2 sleep, and 3 sleep. And the REM, of course, nobody knows what this is about, except when you wake up and have your nightmare dream. But neurophysiology, I never can make sense. Of course, I'm very interested in that because I'm a mind guy. But the results are mixed. So I do not really have clear. You see they're longer than in the awake state, but they're lower than in the N2 and 3 state. So, and that is replicated. So this has been replicated in another data set by us. And indeed, that seems to be a valid marker of the level of consciousness. So now the question is, how does that relate to other measures of EEG? So the typical question which we get from many reviewers who don't know these autocorrelation windows, how they are related to the frequency bands. Do we really need a marker of autocorrelation window which seems to cut across all frequency bands rather than just single frequency bands? And what all our studies show, and you see this often in the supplement then, that you cannot explain the autocorrelation window effect by the single bands. It's really because it cuts across the different frequencies. Yeah, it's more a global dynamic measures, and that's very important, particular for consciousness. So I don't think that there are single frequency bands which can really predict the level of consciousness. So that's why we use a more global temporal approach that cuts across different frequencies and look rather for the structure or relationship. And that is, for instance, in one way measured by your temporal windows / the time scales. So long story short, here I show you the alpha. As you probably know, when you lose your consciousness, it's very interesting. We observed this in almost all our studies. You lose your alpha peak. Yeah, so here you see they are single patients. So this is obviously a healthy awake, typical alpha peak. You know that. Then this is already a patient who loses his consciousness and one of the disorders of consciousness patient. So you already see the alpha peak is slower. Yet another patient reverts the alpha peak to a theta peak. And then there are patients without any peak at all. So we observed that in the EEG of these guys and said, wow, maybe there's something because it's clear that your brain activity is slowing down when you start losing consciousness. It's like in sleep. Your brain activity becomes slow, you doze off. Of course, this talk by Northoff is so boring. I just doze off. Yeah. And my time scales become longer. So, so we investigated in a cohort of disorder of consciousness patients, unresponsive wakefulness, mini conscious state, both this alpha peak, theta peak shift and the autocorrelation window. And first, I show you here the autocorrelation window results. No surprise, they are much longer in the DOC, disorder of consciousness patients, in both frontal and occipital electrode. So this is really a replication. And you know, replication is important because we don't have so many replications in the field of brain-mind. Yeah, so that's a nice thing. So it really seems to be a reliable marker. So then I cut short some of the detailed results here. So then we also investigated the power ratio. This is basically the alpha slash theta or shifted power peak relative to the global power. So we set basically a local temple alpha theta power relative to the overall global power. Yeah, that's what we call by power ratio. And interesting, only that power ratio, not the power, the single alpha or theta power by itself, correlated with your coma recovery scale. So this is a scale for you assess the level of consciousness. Clinically, it's often used. What's the level of consciousness? Includes different measures, behavioral responsivity to stimuli, and so forth. And what we saw, okay, the higher the local alpha theta power ratio is relative to the global, the higher your recovery. Makes sense. If you have a higher alpha peak, you're more awake and so on. And so we all know this, and you react better to external stimuli, meaning lowering your alpha. And then we also linked the power ratio to the ACW, the time scale. And what we saw, the longer the time scale, the lower your power ratio. That is interesting. Meaning, if you have a longer temporal window operating in the background, the lower your alpha peak. Meaning you have more temporal smoothing of your alpha or theta peak. Is basically smoothed by the longer temporal window in the background. Yeah, it's the same. You have a large window in front of you and you don't really see the details. And then you have a small window and you see the small window much, the details through the small window much more when in a larger window. Same apparently in the brain. If you have a long temporal window, your alpha slash theta peak is basically temporally smoothed, decreased, smeared, and basically more flat. So, and that goes together with the left one where we say, okay, now we did a mediation model. We said, okay, how is the power ratio related to the ACW and your coma recovery scale, meaning your level of consciousness? And here we could observe, this is a full mediation. We saw that the alpha to theta to global power ratio relates to the level of consciousness through the time scales. So that really suggests that maybe the time scale have a key role, remember my initial iceberg slide, in mediating basic neuronal dynamics to the level, behavior level or mental level of consciousness. Yeah. So, and then we said, okay, alpha theta peak is about power dynamics, is about power amplitude. How about the other component of the signal in EEG, the phase dynamics, the fluctuations in your phase? So this is what we analyzed here with what is called the alpha frequency sliding, or here mean instantaneous alpha frequency. That goes back to a paper by Cohen, 2014, J Neuroscience, where you basically analyze the phase cycle. You do a Hilbert transform, analyze the phase cycle, and then the peak amplitude. Often it's usually just considered as peak alpha frequency. But here we said, okay, what is really important is your underlying a phase cycle and how that drives your peak frequency. So that's basically a conjoined measure, which you then also can control for. You can take the phase modulus, do the frequency power, and we did all that. So in what we here observed with the other signal component, that your ACW is very much related to the peak frequency. Same here on the left, lower left, you see the longer your time window, the lower your peak frequency. And that again makes sense. It's a temporal smoothing, and basically a longer window pulls down your alpha peak frequency. But note that the correlation, as in the other, is around 0.3, 0.4. You don't get it higher. So meaning there is a relationship, but not the same. Interestingly, lower right, you see that the correlation between the alpha peak frequency and the ACW is positive in the patient with minimally conscious state. So it seems to be the reverse. If you have longer temporal windows, you have higher peak frequency. What that exactly means is unclear, but it suggests there's a really dynamic reorganization in these guys. And that makes sense. Maybe that's a compensatory effect to maintain a certain alpha peak frequency. We currently don't know. But it's clear, again, the basic signal component, your phase, is related to the timescales. So then you say, Georg, is this a real dynamic relationship, or is this just specific for the EEG frequencies? And between 1 Hertz and 180 Hertz. However, we observed exactly the same in fMRI. So I spare you some of the detail. Why is that important? Because on fMRI, we're in the infraslow frequency range from 0.01 Hertz to 0.1 Hertz traditionally. So the question is, of course, and usually fMRI is not analyzed in terms of phase dynamics, but all your functional connectivity is ultimately phase-based. So we applied and adapted the Cohen, the EEG Cohen sliding peak frequency to fMRI, and you can see the details in that paper, and said, okay, how is that related to the ACW, the timescales? And we see a similar relationship. You see here, we have a narrow band passing because you don't want to have too much temporal smoothing of your phase cycles. That's why the narrow band passing. And you see again a quite good relationship in the different infraslow frequency range down here between the ACW and the peak frequency. Same thing here. If you have longer ACW, you have a lower peak frequency, meaning your temporal window seems to somehow again pull down the peak frequency to slower ranges. Make it so. So there you really suggest the direct relationship that your ACW has an impact on the phase cycles, modulates them, or vice versa. And that is indeed then relevant for the level of consciousness. So here, I didn't talk about the topography. This is another topic. And remember, we had a strong convergence between the distribution of the timescales and the unimodal transmodal topography. So here, another student in my group, Andrea Buccellati, who did a very clever thing, both MEG and EEG. So first he said, okay, look, maybe this unimodal transmodal topography is not written in stone, meaning it's dynamic. And that indeed supported by other papers who showed some phase dynamics, how the phase fluctuations in fMRI in both monkeys and humans really drive your network constellation. I always forget the first name, the name of the first author, which is a double name. And what we did here is, okay, we said, okay, we look at the variability of your autocorrelation window. So, and whether the variability of your autocorrelation window is directly related to different topographic states. And that's exactly what here Andrea Buccellati did in a very ingenious way. He said, okay, I do the autocorrelation window variability sliding window approach and show whether that is related to distinct topographic constellation, and did the k-means clustering for different topographic constellation. And he got in both MEG as well as in EEG 4 different main clusters, topographic clusters, according to the ACW variability. You see a more frontal, basically, you see clusters 1 to 3 are different constellations of unimodal transmodal topography. You see this is the EEG data. You see much more detailed in the MEG data in that paper. And the fourth is interestingly no real clustering. And then he did the same thing in the that healthy data, and then he did the same, the distribution of these four different topography, dynamic topography maps in the three different states of healthy, minimally conscious and unresponsive wakefulness state. And remember, state 4 is where you have no much topographic differentiation. Yeah, unimodal, transmodal show similar lengths of time scales, whereas in 1 to 3, you have a real transmodal, unimodal difference between the autocorrelation windows. And then he said, okay, the distribution of the state, and interestingly here, state number 4 is very low. So usually we are often in a state of unimodal, transmodal topography, whereas in MCS and in UVS, you have a very high ratio of your topographic undifferentiated state. Yeah, so you lose often you lose with the increasing length of your ACW. You also seem to lose your topographic unimodal transmodal differentiation. So that again suggests your ACW, your timescales are really also important in shaping your topographic dynamics. And that is different. And then he did a very clever thing. So he said, okay, then I apply different measures for the state transitions between these three different topographic dynamic states and looked for the predictability and the temporal decay. And here you can see is the context tree weighting. He did this for the predictability here. I summarize the things that the memory was, the decay was different between the two groups. And basically that you really have a loss of the state predictability and the memory between these four different topographic states. Cut a long story short, your topographic dynamics is more random in your INT-driven topographic transitions are more random with less memory in the unconscious state compared to the conscious state, meaning you lose your temporal structure. And temporal structure really is a memory, how much you can predict, how much is there a degree of non-randomness in your INT-based state transitions. So how does all that relate to the level of consciousness? So this is a schematic figure, but based on real data, EEG data of the length of your ACW. So the idea, look, for instance, here, this is from Federico Cilio, who's actually also a philosopher and neuroscientist. And so he draws this figure. So here in the awake state, you have different time scales, shorter and longer. So here, now this is your environmental context, the scene about police and the thief. And you see, you need different time scales. You need a short time scale to capture each single word. But you need a slightly longer time scale to link police with stop. Then you link an even longer time scale to link police stop, stop now. Yeah, and you'll never catch me and so on. And this is indicated here. Now, when you become drowsy, your time scales become longer, meaning you lose your shorter time scales maybe for the single word. So maybe the transition between the words cannot be as temporally segregated or differentiated anymore. Yeah. So here, and then your time scales become even longer and becomes blurry. Yeah. And then the time scales are completely long, it's black. Okay, sorry. So, and that's very important. So in a way, the IIT people might now kill me, that there's too much integration here, but you lose consciousness. Yeah, because, and I will show later that your time scales are really important for temporal integration. What is important that you have the variety of different time scale durations for the differentiation. Here you have a very strong differentiation of each word, but also integration. But here it tilts only towards integration without any segregation. Yeah, and as I said, I will later show you more empirical support for those two mechanisms. So that's a tentative thing, but we showed this, for instance, in the case of visual perception, visual cortex in concrete data. So how do I imagine it? I showed you different levels of neuronal activity, and I intentionally, very intentionally, did not a box model. Yeah, I did a layer model because the phase impacts the power slash the amplitude. It's recapitulated, it's nested, and it shapes it. That in turn shapes the timescales. That in turn shapes the topography, and that you saw the outer ring is consciousness. So, of course, I cannot really support this on empirical grounds, but at least and also the organization of these different layers. It's a phase recapitulated shapes in your power, for instance, three phase cycles. Yeah, but they're not just of the different meaning for your mental features. And I showed you the relationship of the alpha power with the timescales. I showed you the relationship of the timescales with the topography. And I showed you in all of that they're somewhat related to the level of consciousness. And you see, I already indicated because the step from the pure dynamics of the timescales to the topography, that might be related to the state of consciousness. So we conceptualize that as a model, dynamic layer model of brain. So I'll probably be a little bit short for the second part because I see time is already running. My time scale is running out. So I keep that a little short because I want to give you a little bit insight into the mechanism. So here I show you one example from meditation, how the link to the mental, because so far you can argue, yeah, Northoff, you showed me some timescales in the brain related to the level of consciousness, but you did not show me that the timescales are manifest in consciousness itself. So here I show you an indirect example. Here we did 3 different forms of meditation. So in the last years, I established strong collaboration with a Center for Consciousness in India, and we get into meditation. And it's unbelievable. The philosophical background is completely different than in the Western tradition. It's a learning experience. It's fantastic. You see me smiling. It's incredible. And they are the perfect people for know the phenomenology, the experience. And that's what we need. So here I show you data, EEG data, from 3 different meditation. So Shunya meditation is where you don't focus on any particular object, neither in your thoughts nor in your external environment. You just try to completely detach. So I often compare that with like a cloud passing by, but you don't attach yourself. There's equanimity, de-identification, and just passing by. Same with your internal thoughts. They just pass by. You don't glue yourself. You don't attribute significance to them. You just stream. That's the shunya. In the mantra meditation, obviously. So, and in the shunya, you can say you need, you don't have particular attentional windows because you don't focus on any particular content. In the mantra meditation, you focus, of course, on the chanting. And then you have the vipassana, so you have shorter temporal windows of your attention. Here, the vipassana meditation, you focus on different bodily organs. Yeah, so you need a clear temporal segregation in your attention because now I focus on my hand, I focus on my shoulder, I focus on my nose. So you need a clear temporal segregation. So you see that different attentional window. So large in shunya, small in vipassana. So now we assume maybe there are corresponding temporal windows in the brain. And that's exactly what we found. So here I show you in the lower results, I show you a long autocorrelation window in the shunya, the long attentional windows where you don't temporally segregate. I show you a very short autocorrelation window in the brain in the vipassana, where you move. Here are the attentional windows, here are the brain windows, the time scales duration, and in the mantra, it was in between. So you see that suggests, we didn't show this, but it suggests different levels of temporal integration, temporal segregation. So that's a suggestion, interpretation of these findings that here you need a clear temporal segregation to focus your attention on the different body parts. Here you don't do any temporal segregation, you just let it flow by. So we did similar things with thoughts. I spare you that. I just show you the main take-home message of that. What we could establish, this was a paradigm about off-task thought. Basically, you're not following my talk. And on-task thought, you're really listening to my talks. And what we observed that in off-task thought, when you don't pay attention, your autocorrelation window is longer. So your inner cognition is slower. Your on-task thought are faster, meaning shorter temporal window. And then we analyze the ACW in long, in block, as well as in trial-based way. As I said, I spare you some of the detail, but what we could really see that longer time scales operate in the background. So you have more off thoughts, whereas shorter time scales more operate in the foreground. You have more on-task thought. And the relation between background and foreground, if your background is closely coupled with the foreground, with your longer time scales are closely coupled with a shorter time scale, you're more likely to have an on-task thought, meaning you pay attention to me. Whereas if your longer time scales in the background are more decoupled from the foreground, you don't pay attention to them. You're in your off thoughts. And this is really the structural equation modeling, and we could really see this. So that, I think, pertains that we perceive the contents of consciousness, like here the apple, in a background-foreground relationship. Yeah? It's not that there's an isolated content like qualia, what is it like to be in one region? No. It operates against, phenomenologically, against a longer time scale background. And that is probably similar so in the brain. So that's the background and foreground, long time scale, short time scale with different layers. Yeah. And that you see, I indicated it here. So this is a background, foreground development. We really now to develop, also operationalize. We have another paper in revision on this and in submission. So that we really on phenomenologically background, foreground, what maybe neuronally, maybe related to longer, shorter time scales. So, and that's the famous perspectivalness, minusness, whatever you say in the phenomenological description. So, you see, I again make my beloved a layer model. As I said, I very intentionally do not do the usual box model with arrows between them. I do a nested layer model. That, if you're from the Asian part of the world, that's very familiar to you. Okay, now let's for the mechanism. So here I show you it's indicated that these time scales are important for temporal integration. So one key feature which we assume that they're also important for matching, meaning the matching between the time scales in your environmental input and the time scales in your brain. So here we did a study on semantics. So we investigated the semantics using of a text, WordNet and as BERT, meaning words and sentences. These are natural language programs. And we measured the fluctuation in the sentence similarity, meaning we measured the timescales of the fluctuation. And we again used the ACW for that. So we use the ACW to investigate the timescale fluctuations of your semantic input and your word similarity. And then you can see that here. And then we link that to the timescales in the brain activity. So you see timescales of sentences, timescales of word lengths, meaning the fluctuations. So, and then we did transfer entropy. So we had the time series of your word similarity, of your sentence similarity, and the time scales of your brain. All three measured in ACW, same method. And what we could observe is similar, is really a direct causal relationship from the time scale fluctuation of the word sentence to the time scale fluctuation of the brain. And here we plot the topography of that typical language areas for both sentences and words. So that's a quite nice fan. You can go into the details. So that suggests that the time scales of your input in your environmental context are directly related to the time scales in your brain. Now, the next step, of course, you said, yeah, Northoff, how is that related to the output, the behavioral output? We're working on this, and we have in other domains papers published on that. So meaning there's a direct timescales of your input, timescales of your brain, timescales of your behavior, mental. So why are timescales so important? Here, this is a schematic illustration from one of our papers. Um, so imagine a robot has different kinds of timescales. Yeah. Now, when you get an external stimulus like music, you have an abundance of timescales. Or look at a movie. Yeah. Now, if your robot has only the the shorter timescales, but not the longer one, the robot will always dance too fast to the music. Vice versa, because it cannot capture the slower timescales, the longer timescales of the music. Now, if the robot has only the longer timescales, but not the shorter, it will always be too slow. Yeah. So that's really in the matching between the input timescales and the brain timescale may be optimal if the brain has a variety of different timescales. And that's probably what is the case. Now, in a way, as a psychiatrist, this is what I see in mania. Mania, you can literally see the measure, the timescales are shorter. The guys are too fast. We are too slow for them. Yeah, so that's why they're always too fast. Look at a manic patient. You would not follow me in my talk anymore if I were manic. Yeah, and the opposite is in depression. If I'm in depression, I speak very slow without any change. You can literally measure the lack of speed, and they're too slow. They're lagging behind. So here you see there's too much integration, there's too much segregation. You need a balance. And that's important for the temporal matching. So now, how can we demonstrate the temporal integration? That if you have a longer time scale, you have more integration. So this is a computational model. Modeling, this is a Chaudhuri-Wang model 2015. This was done by Yazir Katal. And you can see here, so here we had the different regions from V1 to anterior cingulate, 24C, and we stimulated the model with different inputs. Short inputs to V1, and you see in V1, it's perfect, really one-to-one representation of the temporal structure of the input. Now look at the anterior cingulate cortex. It's a catastrophe. It temporally integrates the different inputs into one activity change. That's your longer timescales in the transmodal. So here you have strong temporal segregation. Here you have strong temporal integration. So then we said, okay, maybe this is just duration to the short input. Here's the same for the longer input. We see the same thing. So here you have a temporal smoothing of your signal. You have increasing temporal integration. And then we also measured the ACW of the anterior cingulate cortex in the model. Same here. So this is replicated. And then to keep things short, here Yazir came up with a very clever idea. He said, okay, in the Chaudhuri model, there's a hierarchy index. And he said, okay, hierarchy index from unimodal to transmodal, you can see here. Why not setting the hierarchy index to 0? Yeah, so meaning make all the regions similar. And you see the differences between the visual cortex and your anterior cingulate disappear. So this is with the hierarchy index. You see the temporal integration, the temporal smoothing, and you see the temporal segregation. Now all regions are similar, meaning topographic hierarchies are important. So that's a matching. I think I can spare you that, the exact details. This is the idea why temporal windows are important. We see the same objects in different ways and detailed through different window sizes. Yeah, here in the large window, you see much more background. In the small window, here the purple one, you see much more detailed. Here's the branch. Yeah, but here you don't know that the branch is part of a tree and that the tree is part of the forest and so on and so forth. Yeah, zoom in, zoom out. So last mechanism, which we did, this goes back to work by Yazir Katal and Khan Keskin. So they used the Wilson-Cohen model as a neural mass model and with the DTI matrix. And here show you some differences. This is a simulation of stimulation in the model, basically a task state. and we set the recurrent connections. The recurrent connections are here. This is a recurrent connection within the regions themselves. So it's not the recurrent connection like in the debate about consciousness, but within the region is an intracolumnar connection. And he showed in empirical data, both mice and EEG, that during behavior, the timescales became longer, the ACW became longer compared to the resting state. And he also showed, and that is replicated in the model, and this is also here, the change of the timescale from stimulation to rest directly relates to the variability of the timescales in the resting state. Yeah, meaning the higher the variability in the resting state of your timescale, the less change from rest to task. So that is a replication of empirical data in the model, and that shows us the validity of the model. But what I really want to point your attention to is then you can change the degree of recurrent connections in the model. Yeah, you change the degree of these connections in the model and see how that, affects your ACW from rest to task. And what you observed that you make the recurrent connection stronger, you have longer ACW, but if you make them too strong, your ACW decreases. So it's an inverted U shape. You have a certain optimal range of your recurrent connection where you have an optimal ACW rest task change, whereas you have a less optimal. So that importance of recurrent connections was further supported in another modeling study where we modeled the self. So that's where the self comes in. So we established on a large-scale meta-analysis model 3 different layers of self. So each layer of self is all based on empirical data, large-scale imaging. You have an interoceptive self, here mainly dorsal anterior cingulate, thalamus, insula. Then you have an extroceptive processing. You have insula again. You have a recapitulation of these regions. You have also the premotor cortex, not shown here. It's here. You have the medial prefrontal. You have the TPJ. Extroceptive is mainly pro-processing. For the people who know Olaf Blanke, they did a lot on that extroceptive level of self. And mental self-processing is the typical self-reflection, cortical midline structures. So now in the empirical data, fMRI data, we said, okay, look, we looked for all those self regions together compared to non-self region, and we could see, okay, the self regions show longer ACW, more non-self. Makes sense, more temporal integration in yourself over time, temporal continuity, blah, 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 blah. So now the interesting step. Now he tried to model that in the Wilson-Cohen model, large-scale Wilson-Cohen model. And he said, okay, these were the empirical results. So he measured the ACW also in the transmodal self regions, in the unimodal self regions, unimodal non-self, transmodal non-self. You could really see a gradient that from unimodal non-self, unimodal self, transmodal non-self, transmodal self, your ACW becomes consecutively longer. So now he said, what do I need to do in the model to replicate that kind of topography? So meaning with which kind of physiological parameters I need to play. So here he fixed the intra-regional recurrent connection as well as the excitation. You don't get any such in the model ACW, any topographic hierarchy. Then he changed the level of excitation, but the recurrence was still fixed. You get somewhere, but not optimal. The closest was when he really changes the level of recurrent connection and your excitation together. That's closest to this one. So that suggests that excitation, the degree of neuronal excitation, and your intracolumnar recurrent connections are key. Schematic figure, what does it mean? So you have more excitation, more excitatory recurrent connections in the cells. That leads to longer ACW, longer time scales. And that means your what we call self-related processing, maybe an intra-regional recursive processing. Longer ACW, more recurrent connection, meaning stimuli which you perceive in relation to your own self may be related to the longer duration of the stimuli mediated by ACW and recurrent connection. So coming to the end, I hope I could make a case, and you can see here that maybe the duration of your time scales connects the neuron with the mental level through the ACW, through the recurrent connection. So, conclusion number one, I hope I could make a case here. Timescale shapes the mind, particular consciousness, and also self in the last paper through recurrence and temporal integration. So, in a larger concept, we say that timescales are key, both in neuronal and mental, and that for me, consciousness and mental features are intrinsically temporal. So here I show you, I don't go into that. That's basically the conceptual background model of the concurrency, for which we have a lot of empirical support from other study as well as own studies. Speed, for instance, depression, your brain is too slow, your movements, your thoughts are too slow, and so forth. But it's not a one-to-one correspondence. It's a complex. It's not just simple one-to-one isomorphism. That, I think, is an illusion of the philosophers. Please forgive me. Yeah, I think this is not plausible. Yeah, so that's why we speak of a complex correspondence. And again, you see my beloved layers, because I think it's really a nestedness layers. And you see I integrated that here. And very key, which is often neglected in the current debate about consciousness, is this one. Yeah, you need this matching. Remember, I spoke of a matching of the timescales of your brain with the timescales of your environmental context. And you see, I try to show some of that path. And with that, I come to an end. Thank you very much. I hope my talk has also connected with your mind.
Thank you. Thank you. It was really good. I have a full page of notes and questions. But yeah, it's now